Today we have a computational tutorial on LSTMs and TensorFlow. So the two people that will be talking today, the first is Nick Locascio, is that how you say your last name? And he's a men's student in CSAIL working in Regina Barsley's group. His current research applies deep learning to diagnostic mammography screening. And then the second speaker that we have is Harini Suresh, and she's also a men's student in CSAIL, and her research uses LSTMs to model physiological time series. Great, okay, so let's get started and be exciting.
Hi everyone, I'd just like to thank Janelle for inviting us out here and organizing this event. Very excited for it. So, LSTMs and TensorFlow. The outline of this talk and this tutorial series is 4 parts. We're first going to just start with a brief overview and summary of neural networks. Harini's going to talk about sequence modeling with LSTMs. We're going to talk about TensorFlow fundamentals. And then part 4, you're going to dive in and actually build LSTMs in TensorFlow to classify airline tweets as positive or negative. So a brief overview of neural networks first. I'm sure you've all seen diagrams like this. There's some nodes connected to some other nodes. If we just kind of dive into one of these nodes, it's called the perceptron, and essentially what it does is it takes some inputs, multiplies by some weights, sums them, and applies a nonlinearity. So to break it down, we take our inputs as some x vector, we multiply by some weights, which is our w vector, we sum them, we add a bias term, and then we apply a nonlinearity to this. And we can just kind of rewrite this as a matrix multiplication. And let's dive a little into this activation function, g of whatever our input is. So there's a lot of different activation functions. One that you might have seen before is called a sigmoid activation. And what this does, it applies a nonlinear transformation to the data. There's a graph of it on the bottom left. And the key thing here is that there's lots of different activation functions that you might come across and you might see. There's things like sigmoid, 10H, things like ReLU, which is very popular now. And the key idea here is that they apply a nonlinear transformation to the data. And the reason this is important is because our data is most of the time going to be nonlinear. And if we want to make decisions and draw decision boundaries around this data, we need to build models that have nonlinear capacity in them. So as you can see, linear models can draw straight lines, and nonlinear you can have more complicated decision boundaries. So if we were just to look at the forward pass of a perceptron, and we pass in some inputs as numbers and multiply by our weights, and we add them up, apply our nonlinearity, and we get some output number. So that's just the perceptron, but if we want to build entire neural networks, we need to kind of composite these things together, right? So if we're going to just simplify our diagram a little bit, as we just have some inputs and they go to some node. And we can write multi-output perceptrons where we have 2 perceptrons that lead to multiple outputs. And we can even stack them together to create neural networks like this. So this is an MLP. It's the smallest neural network you can technically create. And we're going to simplify a little bit more to get to our final diagram. We just replace all those connections with an X. And if we want a deep neural network, we just stack many, many, many of these. And that took you from perceptron all the way to the diagram that you see a lot. So if we want to go about and train these neural networks to do tasks that we want them to do, and in any machine learning model, you have to train your network or your model. So if we have our loss defined as some function, if we call it j of theta, we want to define our objective to minimize this loss by adjusting our weights, adjusting our theta. So remember, theta is just kind of the weights of our network. It's what parameterizes our network. And we do this with something called stochastic gradient descent. So if we think of our loss function as a function that relies on our weights, so here theta 0, theta 1, we just kind of pick any random initialization. We start with any thetas, any weights, and we have some loss for that. We can compute the gradient to move in the direction of maximum descent. And we want to minimize this loss, so we kind of iteratively do this and move our way kind of down this curve until we reach some convergence. And this is called SGD, or stochastic gradient descent. And just kind of formally, there's this idea of an update rule where you apply this gradient. But let's just dive a little bit into how do we actually calculate this gradient, this dj theta of d theta. And we do this with something called backpropagation. So with backprop, you want to find how your loss changes with respect to a specific weight. So here, where you want to look at how our loss changes with respect to weight 2. And to do this, we apply the chain rule. So we know it relies on how our loss changes with respect to the output. And we also know that the output relies on how weight 2 changes. And similarly, if we want to do this for weight 1, we just apply the chain rule, and we apply the chain rule again. So that was just kind of a brief overview and summary, just to refresh your memories on neural networks. And Harini is going to be taking off from here, talking about how to build off of standard neural networks to create recurrent neural networks and LSTMs. So I'll hand it off to her now. Yeah.
Why is it that, like, picking any arbitrary nonlinearity, like, you compose those into whatever cool nonlinear function you want?
Yeah, sure. So I think the key idea is with many layers, you're going to learn the weights necessary to kind of draw the decision boundaries that you want. So if you were to have a nonlinear transformation, if you just take times by 1, and you stack these many layers, it's still going to be like a fully linear function. No matter how many layers you have, you still need to introduce some nonlinearity in the layers to have a nonlinear model. So yeah, I think it's a little crazy sometimes if you look at something like ArrayLu. I'll just go back to this real quick. ArrayLu is the simplest nonlinearity that you could think of. It's 0 everywhere, and then it's just kind of this linear function. And surprisingly, it actually works really well, and it's most popular now. So it's a bit of kind of an engineering question, but it works really well. And I think the key thing is people used to use sigmoids a lot because they thought it was a cleaner, more smooth gradient. But with something like ArrayLu, it's not as clean, but you still get the results that you want.
Now I'm going to talk about sequence modeling, and basically what I'm going to talk about is why we would want to model sequences with a recurrent neural network in the first place, and then go into some of the motivation for an LSTM specifically, which is just a specific type of recurrent neural network. Okay, so first of all, what exactly is a sequence? By sequence, I just mean an example that consists of multiple values, and this can be a variable length set of values, and future values depend on previous ones. So this is something like a sentence, a function, or a speech waveform. And so neural network models, specifically RNNs or recurrent neural networks, have had a lot of success in this area, and you've probably encountered asking questions to Siri or Alexa or using Google Machine Translate, and the state of the art in both machine translation and question answering tasks is based in RNNs. Okay. So now, let's say we want to go about and model a sequence. Well, the first thing we need to think about is how exactly are we going to represent our sequence. So in order to feed something like a sentence into a model, we need to represent it as a vector of numbers. So one thing we might think about first off is, okay, well, how about we just represent the sentence as a bag of words? And in a bag of words, we just have a vector, and each slot in the vector represents a word, and the number in that slot represents the number of times that word occurs in the sentence. So now we have a fixed length vector representing our sentence, and we can feed that into a model and make a prediction. So a problem you might notice about this is that the bag of words representation doesn't preserve any type of order in the sequence. So for example, these two sentences, the food was good, not bad at all, and the food was bad, not good at all, have the exact same set of words, so they'll have the same exact bag of words representation. However, they mean completely opposite things. So you can see how it might be difficult for our network or our model to get semantic meaning out of sentences when we're representing them like this, because opposite sentences which mean opposite things can have the same exact representation. Okay, so we know now that we want to preserve order to encode meaning. So the next thing we might think about is just having a longer feature vector in which we maintain order. So in this case, we just have many slots within our feature vector, each corresponding to a word. And so the first 5 slots here correspond to the first word, and the next 5 correspond to the second word, and so on. So now we're maintaining order within this vector. And now we just have a longer vector, we feed that into a model and make a prediction. However, in this case, it's actually difficult to deal with different word orders. So in this example, on Monday it was snowing versus it was snowing on Monday, these actually mean the exact same thing, but they have entirely different representations in this model. So the problem with this when we're dealing with sequences is that oftentimes sequences operate according to the same rules across the sequence. So in the example of language, there are certain rules of grammar and language that apply no matter whether we're at the beginning of the sentence or at the end of the sentence. And when we have things like this, since we're not sharing weights or we're not sharing parameters across the entire vector, if we learn something about language at the beginning of the sentence, we're going to have to relearn that at the end of the sentence. So because our vectors are entirely different for different things, this is also a problem because we're going to have to relearn things across the entire sequence. Okay, so we want to deal with this problem, and so something we might turn to is something like a Markov model. So in this case, we don't have to relearn anything because we have a set of rules and a set of states and a set of transitions. So here we know that no matter where the word I appears in this model, there's a 0.66 chance that it's likely to be followed by the word like. So whether this appears at the beginning of the sentence or the end, we have these rules encoded in the Markov model. The limitation with this, however, is that we're assuming that each state depends on the previous state, or a finite set of previous states, which is also quite limiting. So for example, in something like language, if I showed you the following sentence, in France, I had a great time, and I learned some of the blank language. Well, you and I as well probably to figure out what word goes in that blank. I looked way far back at the word France, and then I looked ahead at the word language, and I can pretty much tell that the word that should go in that blank is French. However, if I just looked at the previous word, the, I would get very little information about what the next word should be. So in complicated sequences like language, it's really important to be able to model longer-term dependencies and keep track of things that happened far back in the past. So something like a Markov model will often not perform very well in generalizing to sequences like language. Okay. So this provides like a brief motivation for why we may want to use a recurrent neural network to model sequences. So as a review, the things we want to solve are we want to maintain word order because this is important to semantic meaning. We want to share parameters across the sequence so we don't have to relearn rules across the entire sequence. And lastly, we want to keep track of long-term dependencies and remember things that happened far back in the sequence. Okay, so this is what an RNN looks like. You might notice that it looks really similar to the neural network that Nick introduced in the previous part, and it is. There's just a slight difference in what the hidden nodes are computing. They're computing a slightly different function than before. So let's take a look at this one hidden unit to see what it's doing. So before, the hidden unit computed a function of the input times some weights and then a nonlinearity and produced an output. Here it's doing the exact same thing, except in addition to a function of the input, it's also producing a function of its own previous output, which we call its previous state. So in this way, it's able to remember things it saw in the past. So if you look at the last equation, you can see that the next output of the hidden unit is really similar to what you saw before. It's some weights multiplied by the input, but it's also some weights multiplied by its own previous output. And we just keep doing that across the sequence. At every point in the sequence, we feed in a new word and the previous output, and we compute the new output. So because of this, a really common way to view a recurrent neural network is by unfolding it across time. And by time, I don't necessarily mean actual time, but just where we are in the sequence. So here you can see clearly that at each point in the sequence, we feed in the next value and the previous cell state, and we compute the next cell state. So this is the key to why this is different, because we're keeping track of a state within the cell, which was not happening before. Before, a normal hidden unit only knows something about the current example. It doesn't know anything about the examples it's seen before. Okay, so some things to notice here are that W and U, those parameters, stay the same throughout the sequence. So this solves one of our problems, which is that we want to share parameters across the sequence. So once we learn something about grammar, say, at the beginning of the sentence, we know that that also applies later in the sentence, and we don't have to relearn that. The other thing to note is that S sub n, the cell state at time n, can contain information from all the past time steps. So this solves our problem of keeping track of long-term dependencies, because you can see that since the state at time 0 feeds into the state at time 1, which feeds into the state at time 2, at any time n, we have computed a function of all the previous states. Okay, so now I'm just going to, oh, sorry, yes.
So sorry, each hit unit, in addition to its weight matrix, its weight vector, and the x input vector, also gets only its own input, or only its own previous state as input, or a vector of.
It gets its own previous state as input, yeah. All right, so I'm just going to go through some possible tasks that you could do with this, specifically applied to language, but this is easily extended to other types of sequences. So one possible task would be something like a language model. And in a language model, we are basically training the recurrent network on a specific corpus of language. This could be something like English or French or something even more specific, like all the works of Shakespeare. And in doing so, we are training it to be able to predict the most likely next word given what it's seen before. And in doing so, we can then produce, get outputs from that network and produce language that looks really similar to the input text. So this is something that's produced from a language model that was trained on all the works of Shakespeare, and you can see that it looks pretty similar. Okay, so how exactly it does this or how that network would look is something like this, where we have an input at each time, but in addition to producing a state at each time, we're also producing an output, and we just do that by multiplying by another set of weights. And here, each output is a probability distribution over the most likely next words, given what it's seen before. If we're training this network, we would have some loss function based on how similar that sequence is to the sequence we were actually trying to get out. And if not, if we've already trained the network, then we can just continue creating outputs to generate sentences like what you just saw. And you can train a language model using anything. So this is a funny example that you can find more examples at the URL at the bottom, but this is a language model that's been trained on the King James Bible and the Structure and Interpretation of Computer Programs textbook, and it produces things like, had it not been for the singular taste of old Unix, new Unix would not exist. Okay, so another task, a possible task, is something like classification, and this is what's in the tutorial later. So this is something like if we have a bunch of tweets and we want to determine, okay, the tweet on the top is negative and the tweet on the bottom is positive. So this is really similar. It's just we have a network and then we're producing an output at the very end. And this is a probability distribution over classes. It could be something like negative, positive, negative, and neutral in this case. And something to note here, which is kind of something that will come up again a couple times, is that we are making this prediction about the entire tweet based on just the cell state at the last time step, which means that this network is creating a representation of the entire tweet based on at just the last time step. It's not just information about the last input, it's information about the entire tweet, because from that it's able to make a prediction about the entire tweet. Okay, so the final task I want to go over is machine translation, and this is called an encoder-decoder model because it's actually made up of two RNNs. The first one is an encoder, and it basically takes a source sentence, encodes it into some fixed length, and then we take it takes the source sentence into an encoder network, and then we take the last cell state, feed that in as input into the second network, which is basically just a language model for a different language, such as French. And then given that last cell state from the encoder as the words that we produce, we can produce an output sentence in a different language. So notice here, again, that we're treating the last cell state as a representation of the entire source sentence. Basically, what that cell state has to do is encode the core meaning of the first sentence that we saw, because from that, it's able to produce a sentence in a different language that means the same thing. Okay, so now I just want to talk about how we would actually go about training a recurrent network. So it's really similar to what Nick talked about. It's just backpropagation. It's just that there's an additional time dimension. Okay, so just as a quick review, in backpropagation, we take the derivative of the loss with respect to each of our parameters, and then we move the parameters in the opposite direction of that derivative so that we can minimize the loss. Okay, so we have a loss at each time step in an RNN because we're moving through time, and so it's pretty simple. All we do is just sum the total loss for a particular parameter is just the sum of the losses at each time step. And since we have a loss at each time step, we also have a gradient at each time step, and the total gradient is just the sum of the gradients at each time step. Okay, so to kind of go into this, we can just try it out for a particular weight W. So this is just for one parameter. How would we calculate the gradient? So we know that the gradient for the derivative of the loss with respect to W is just the sum of the losses at each time step with respect to W. So we can focus on a specific time step, and then you would just do that for all the time steps and then add them up. So let's take time step 2. We want to know what is the derivative of W with respect to the loss at time step 2. In this case, that's denoted as J2. Okay, so again, we just use the chain rule. The loss at time step 2 depends on the output, which is Y2. That depends on the cell state, which is S2, and that depends on W. So there we use the chain rule to get the derivative of the loss with respect to W. But you might notice that we have this last term, and it's the derivative of the cell state at time 2 with respect to W. If we look a little closer at this, we can see that the cell state also depends on the cell state 1, and that also depends on W. So we can't just treat that last term as a constant. We have to expand it even further. Okay, so to figure out how exactly we need to expand that, let's look at how exactly the cell state at time 2 depends on W. Okay, so we know that W feeds directly into it. That's one way. We also know that the cell state at time 2 depends on the cell state at time 1, and W feeds into that. We also know that the cell state at time 2 depends on the state at time 0, and W feeds into that as well. So we end up with this summation where we are counting, and the reason we have to do this, remember, is because of what I said before, where the cell state at any time depends on the cell states at all the previous times. And since we're sharing parameters, we know that those weights, W, contribute to the error at time 2 based on how they contribute at time 1 and at time 0 and all the previous time steps. So what we're doing here is basically just counting the contributions of W to the error at all the previous time steps. So I'm just writing this as a summation here. This is just this sum written in a summation form. All we're doing is getting the derivative of the state to all the previous states, and then the contribution of W to that previous state. And this is just generalized to any arbitrary time step. Okay, so you might guess since this was kind of complicated, that RNNs might be hard to train, and they are. And so just to kind of go into a little more into that, RNNs are hard to train specifically because of a problem that's called the vanishing gradient problem. And this comes about from that chain rule product that we were doing. So this is just the same summation from before when we're calculating the derivative of the loss with respect to a specific parameter, in this case W. Let's take a closer look at this one term, and this is the derivative of cell state to each of the previous cell states, so we can count the contribution of W at each of those times. So from our previous network, if we're looking at the contribution of W at cell state 0, we know that we have to do the chain rule back to state 0 and then count the contribution of W at state 0. Okay, so that's fine. That's just a chain rule of two things. However, if we were, say our sequence is really, really long, and we were calculating the loss at the very last time step, we would have to back propagate all the way back to the previous time step, which means we would have to, that chain rule would become really, really long, because we're going to have to chain rule all the way back to the first input in order to get the contribution of W at the first time step. So as the gap between time steps gets bigger, this chain rule product, just gets longer and longer. And okay, so you're probably thinking, okay, fine, why does that matter? Well, let's look at what are each of these terms? Each term, if you notice, is the derivative of a cell state at time n with respect to the previous cell state. And if you remember, cell states depend on the previous cell states by a function, by being multiplied by a weight, and then they have an activation function applied to it. So each of those derivatives are going to be a series of weights and derivatives of activation functions, because we're just taking the derivatives. But what you really want to get out of this is that those are both small numbers. Weights are usually normalized. Weights are usually drawn from a standard normal distribution, and the derivatives of our activation functions are pretty much always less than 1. So what we're doing in this chain rule product is multiplying a lot of small numbers together. And remember, the bigger the gap is between time steps, the more small numbers we're multiplying together. So because of this, errors due to farther back time steps have smaller and smaller gradients because they have to pass through this huge chain rule in order to be counted as part of the loss. So remember that in backpropagation, we shift our weights according to that gradient. So if we're shifting our weights according to the gradient, but the errors from are counting less and less in the gradient, then we're going to be shifting our weights so that basically so that they only are listening to the errors from very close by. They're not going to be, that the errors from very far back will not count as much in the gradient. And because of that, our parameters are going to become biased to capture short-term dependencies, because those errors will be the most prominent in our loss and in our gradient. Okay, does anyone have any questions before I keep going? Okay. Yeah, so this is just reiterating what I said, which is that since the parameters are being biased to capture shorter-term dependencies, we're running into the same problem that we had before, which is that in this sentence, for example, if I'm trying to model language and predict the word that goes in that blank, it's going to be hard if my parameters are biased to short-term dependencies for it to know that that word is French, because it has to go all the way back and see the word France. Okay. So now I'm going to go over some ways that you could deal with this problem and some ways that are commonly used in practice. So one way is by choosing the right activation function. So Nick mentioned there are some common activation functions like hyperbolic tangent, sigmoid, or ReLU, and these are the derivatives of those functions. So if you remember, one of the reasons why that chain rule term was so tiny is because there were a lot of derivative of activation function terms that were in that big long product. So if we're choosing an activation function like a hyperbolic tangent or a sigmoid, you can see why that would be, because the derivative is pretty much always less than 0. So we're multiplying a lot of small numbers together. However, if we choose something like a ReLU, you can see that its derivative is 0 when it's less than 0, but otherwise it's just 1. So if we choose that, those derivative terms aren't going to be shrinking the product. Another thing that we could do is initialize our weights differently. So the other term besides the activation derivative was a bunch of weights that we were multiplying together. And I mentioned that those are usually less than 1 because they're drawn from a standard normal distribution. However, if we instead initialize our weights to the identity function, then those multiplications would at least take a step towards preventing that product from growing smaller very fast. Okay, so the final solution, which is really effective, is using something called a gated cell. And this is all an LSTM is. It's just a recurrent unit that uses several steps of logic gates to control the flow of information through it. And this helps because with a gated cell, we have these gates that decide what information flows through in full and what information gets multiplied by weights and activations and stuff like that. Okay, so I'm going to go through a high-level overview of what the LSTM is doing. There are a lot of equations that determine what the LSTM does, and if you're interested in seeing those later, just come talk to me and I can direct you to other resources. But right now I'm going to go over a more high-level overview of conceptually what the LSTM is doing. Okay, so the first step we have is in which we forget irrelevant parts of the previous state. So let's say I'm modeling language and I see a new subject. I might choose to forget the previous subject because I know that the next word will be conjugated according to the new subject. The next step is that I want to selectively update my cell state values. So since this is a recurrent network, we're keeping track of a cell state. And so I might choose, if the new subject is masculine singular, I might choose to encode that information in my cell state. But if there's something I think is irrelevant, I might not update the cell state to remember that. Finally, I want to output certain parts of the cell state that I think will be relevant to the output at this time step. I might not choose to output everything, however. So for example, if in my cell state is encoded that I have previously seen the word France, but I don't think that's going to be relevant to this particular output, I'm going to keep that in the cell state but not output it. And this is all just done with a series of logic gates that multiplies each input by some number to determine how much of that input we keep. Okay, so as a brief overview of why LSTMs help us with the vanishing gradient problem and make it easier to keep track of long-term dependencies, that forget gate, while it allows you to forget things, it also allows you to remember things. So you can forget certain things completely that you think are irrelevant, but you can also remember things completely. So we're multiplying at each time step by some tiny set of weights. We can choose to, the forget gate can learn if there's some important information to remember it entirely. So that weight would be a 1, and we wouldn't be multiplying by a lot of tiny weights. The second thing is that in the update step, in the middle step, we update to the new cell state based on addition. It's an additive function. So S sub j depends on S sub j sub 1 through addition. So when we back propagate, it doesn't turn into this huge long multiplication. Okay, so does anyone have any questions? You can also ask me about it afterwards if you do. Okay, so yeah.
Yeah, I have a question about the one solution to the vanishing gradient you were talking about. So you're saying that if you initialize the weights to the identity, then that solves your problem. But like once you take like a single step, aren't you already into a space where all of the weights are be like small again, or am I?
Yeah, so the weights will be updated. They're not going to stay as the identity. You're right. But if you initialize, but it's surprising how much a good initialization can help, because once if we start moving really slowly at the beginning, it's possible to get into local minima or not train properly. So if our first couple of steps are really good, that can make a big difference. Okay, so I'm just going to wrap up now and go through one example that we saw before. Yeah. Yes. Yeah. So I forgot to mention that all of these weights, the forget gate weights, the update weights, these are all learned parameters. So the LSTM is actually harder to train. In this case, it takes longer to train because there's so many more parameters. There's not, if you remember in the simple RNN, there was just those two weight matrices, but here there's a lot more parameters, which is correct. However, it's also easier to train because while parameters, if we train it for longer, it's easier to learn. It trains better, basically. It learns better things about our sequences. Yes.
So the gates are used to multiply weights?
Mm-hmm. Yeah, so I can show you the full pictures if you want to come see. There's several gates and several additions. So basically each gate computes a function of our input and our previous cell state to determine what to remember and what to forget. But yeah, they're just multiplications. Each part of the input is multiplied by some value between 0 and 1. And the thing is that it can be completely at 1 or it can be 0 if we want to forget certain things or remember certain things.
Okay. You have a slide or two that could give us the full set of equations for an LSTM?
Yeah. Can we talk after I'm done? Yeah, and then
I guess, but I mean, we're all here to learn about LSTMs.
okay. Maybe when I'm
Recurrent networks now, but not so much about LSTMs.
so maybe once I finish these slides, then I'll put those equations up. Okay. All right, so just to go back to our model of machine translation, we can replace all of these with LSTMs, which is what's typically used in practice now. And one thing that I just want to go back to that I mentioned previously is that a fixed length encoding, if you remember, we are trying to decode our encoder sentence based on this fixed length encoding, which might be okay for a short sentence like the dog eats, but say we're trying to translate a long sentence. That's going to be pretty limiting. It's going to be hard for us to make a representation of our entire encoder sentence in that single last cell state. So one thing we might do, and this is something that's typically used, is called attention. Where we create a weighted vector over all of our previous cell states, paying attention to the cell states that we think will matter most. So for example, when we're decoding the first word, we might choose to place more weight on the first word of the encoder model. And when we're decoding the second word, we might choose to place more weight on the second state of the encoder model, while placing some weight on the other states as well, because those might be relevant for context or for tense or something like that. And these weights are also just learned parameters of the network. Okay, so now there's lots of different things you can do with LSTMs and recurrent networks. So you can extend these models to time series and waveforms, not just language. You can generate complex models to generate text or books or code. Self-driving cars, the way that they park is actually, in some cases, through LSTMs to model motion. You could predict stock market trends or summarize things. But yeah, so I wonder, do you want to go through TensorFlow first and then
Do you want to find the equations, or?
Why don't you go through this and then I'll pull them up on my laptop.
So to prepare for part 4, where we're going to be actually building LSTMs to classify tweets as positive or negative, I'm just going to give a brief introduction to TensorFlow for the uninitiated. So TensorFlow is a deep learning framework, and one of the reasons you might want to use a deep learning framework rather than kind of rolling your own is that you get a few advantages. One of which is GPU acceleration. So your code runs a lot faster. The second is automatic differentiation. So all those derivatives and gradients that you saw in the previous lecture, you don't have to think about them too much. They kind of get handled for you as long as you express your function as some differentiable function. It can differentiate automatically. The third is kind of code reusability, and the fourth is anything that speeds up your idea to implementation to results time is just going to help your research. So there's a bunch out there. There's Cafe and Theano, but we're going to be talking about TensorFlow today. And just kind of one of the core principles of TensorFlow is this idea of a tensor. And if you've ever used NumPy, it's actually pretty similar. So in NumPy, you can kind of make arrays. You can initialize them as zeros or as ones. Very similarly, in TensorFlow, you can just do tf.zeros or tf.ones. And you could do operations like sum and get the shape. And pretty much anything you could think of in NumPy, you can also express in TensorFlow. The other core principle of TensorFlow, it's kind of 3 steps. Like your first is to create a session which contains all of your graph information and all of your weights. The second is to actually define your computation graph. So TensorFlow is generalized to any computation graph. It doesn't have to be a specific neural network. And the third is that once you have your graph set up, kind of feed your input in and then get the results, get the output out from your graph. And this is something called evaluation or running your network. So sessions are kind of just encapsulated in the session object. So there's a couple of different ways to make a session. So in this tutorial, you'll be using TF interactive session, but typically if you're doing like research into individual files, you'll just initialize a session with like tf.session. And the second core part is the graph itself. So this is like a very simple computation graph where we have some inputs A and B, and we're just going to compute some output E at the end that is kind of a composite of these different functions. And we can express any graph in this way. So just to dive a little deep into what a graph is actually made of, so there's different types in TensorFlow. So when we want to feed input into a graph, we kind of reserve a place for it. It's called a placeholder. And essentially, you can create your placeholder. So we have A and B, and they're accepting some input. And we can also create constants. So if you look at the node K, this is just kind of a constant. It's a number. And then the blue ones are operations. So we can add, we can subtract, we can multiply, we can do any differentiable operation we can perform. And we can even do non-differential stuff like taking maxes and things. So once we have this kind of graph created, we want to actually run this graph. We want to feed in some input and then get our output. So the way we do this is we do session.run, and then we pass in the node that we want the output for, and then we pass in any inputs as part of this feed dict object. So to break this down, the first one, we want to evaluate the output E for input A and B of certain values. And we don't have to evaluate the last one. We can evaluate any node. So we can evaluate C, and we can also evaluate E and C at the same time. So moving from a very simple graph to building a neural network isn't that many steps. So the previous one was a pretty constant computation. You fed in some input, and you got some output that wouldn't change. But if we're building a neural network, we need our graph to change. So we can't use constants anymore. So instead, we use something called a TF variable. So we can create variables. They're just kind of matrices of numbers. We can initialize them as zeros or as kind of random normal distributions or as identity matrices. TensorFlow offers a lot of different initialization functions. And the key thing here is we're making this array of numbers, but they're able to change and they're non-constant. So if we were to build a neural network graph, so this right here is just a perceptron classifier where we have some input x. We're going to multiply that x by our weights w, add our bias, and then apply some nonlinearity function to it at the end. And this is how you would create it in TensorFlow, just the code to do so. And note that we're TF variables for the weights and the biases. The next step is we want to add our loss function, so we want to train this. The cool thing about losses in TensorFlow is they're actually graph computations. They're part of the graph itself. So we can express them in TensorFlow methods. So here we're just using a sigmoid cross entropy loss as our output. And the next part is we want to actually optimize. We want to train our network. So we can create, there's lots of different options for optimizers. There's stochastic gradient descent. There's things like atom optimizer. There's lots of different options. And we can run this optimizer. Our optimizer is also an operation in the graph. So we do the same thing where we do session.run. We give it the optimizer node, and we pass in our inputs, our x inputs, and then our y label output, because we want to compute the loss between the two. So that's just kind of a brief overview of creating a graph, running the graph, training your graph. I'm also going to just dive a little into some useful features of TensorFlow that are useful to know about before we start the tutorial. So one of the coolest parts of TensorFlow is this tab. So you can actually dive in and see, once you create your network, you can actually visualize it and see what it looks like. This is really useful in debugging to see like what you created if it is actually what you thought you created. So it's really good to see the actual computation graph that gets built by your code. And you can kind of dig in, click around, and see what's happening in your network. The second is it offers lots of support for logging your results and your loss, so you can see your training and convergence time. And the way you use TensorBoard is you just kind of run it with in the command line, but you want to prepare these outputs. So you use something called summary logs. So to create these graphs, each of these is a summary log, and each kind of point on here is a graph operation that was run to save a number in a summary log. So the way we create summary logs is with tf.summary. We can use things like scalars. You can make histograms as well. And essentially, as you run your graph and update it, it's just another part of your graph that gets run, and it writes out to a log file. The second really useful feature of TensorFlow is something called name scoping. So here, we create a variable v, but it's within the foo, which is in the namescope bar. And we see that the name of our variable v is kind of foo/bar/ the name of the variable. And this is really useful for a few reasons, one of which is actually sharing your weights. So if you want to kind of build a graph, but run it over multiple different inputs at once, and then kind of aggregate those results, you don't want to like create the same graph over and over with a different set of weights. So you want to be able to share the weights between the same graph instances. So you can do something called tf.getVariable to share your weights across different variables. Okay. The second thing for name scoping is it allows you to kind of compositable and more clean code. So we can take all that code that we had written earlier to kind of build a simple neural network, and we can put this all in one function called makeLayer. And if we did this in the naive way without variable scoping, all the variables would kind of clash in their name. So instead, we can kind of create this variable scope, which keeps things clean into kind of different layers by having different scopes. And we might do it something like this. And when you use variable scoping, it actually gives you cleaner graph visualizations. So this conv2 that you look at here in the center, this is a layer somebody made, but they passed in the scoping of conv2. And then within conv2 is all the inner operations, but it gives you a lot cleaner visualizations as well. The next part is, it's great to train these things. Yes?
Does variable scoping only affect variable names, or does it also affect the actual structure of the computation?
Yes. It does not structure the computation. It may affect the way that your weights are shared, though, because essentially what tf.getVariable does is it looks up in the session this specific key, and it'll get the variable for that key. And if it doesn't exist, it'll create it. But if it already exists, it'll grab the exact one. So it's great that we can now train our networks, but it's great if also we can save them and run them later. So there's an idea of checkpointing. And basically, you can create this saver object, and you can save your actual session to a checkpoint. And then when you want to run it again later, you can just kind of load this session. So you create a new session, but you restore it. And it basically takes your entire graph and all the weights associated with it and just dumps it back into the environment, and you have everything that you previously had, so you can eval your model and dig into your weights and see offline what was going on. TensorFlow is also useful as the core of many other frameworks. So if you've used like Keras or TF-Learn or many others, TensorFlow is the underlying code that's being used. So it's very useful to understand kind of the core of what you're using if you end up using one of these higher level frameworks like Keras. So we'll be transitioning into part 4, which is actually the tutorial. So you'll be, again, using LSTMs to classify tweets as positive or negative. I think Harini wanted to bring up the slide of LSTM equations. Is that ready?
Go to the next slide.
Okay. Oh, wow. Wait. Do I have to refresh? No. Oh, that was quick. Do you want to do this?
Why don't we start the tutorial, and if someone wants to ask me questions, then...
Okay.
But it would be nice to, if you walk us a little bit.
Okay.
Yeah. Yeah, they're pretty complicated. Do you want this?
Okay, so basically what we're doing is we're multiplying the input. We get a function of the previous cell state and the input, and we multiply that by element-wise by a sigmoid function. And the sigmoid, so you can imagine that this input is some function of the previous cell state and the current input, which is a vector. We multiply that by a vector of numbers between 0 and 1 because it's a sigmoid. And so that's the gating that we're talking about. We're multiplying each input by some number between 0 and 1. In that way, we're deciding what to keep. The way that, yeah.
Sorry. I was wondering what's about this question. We're actually in the wrong room. Turns out the room is reserved, this room is reserved for another group. That's why there's all this noise.
Oh.
We have to move to 36.
We're not, we switched rooms, so we're fine. Yeah, we have this room.
Not putting to large crowd of people expect to get in here now. The other room is completely free. It's the one that's reserved. We may need to.
WF is a set of weights for that gate. Yes.
Yeah, so we add the previous hidden state and the new input, multiply them by some weights, and then we gate that. So we can choose to pass that fully through if the forget gate activation is a 1. Otherwise, we can choose to fully fit it. In that way, we're making the activation function for the input essentially whatever the forget gate activation is, and that can be the identity function.
So are there essentially 4 weight matrices within the LSTM cell?
Yeah, so we have weight matrix here, and yeah, 4. For the input gate, the forget gate, the update gate, and the output.
Sigma is secret one or 0.
Which so this is a sigmoid function. Yeah. So it's a number between 1 and 0.
So the difference between a gate and just like different layers concatenated where you also multiply by a matrix and then you pass it to a sigmoid, which is basically what we were already doing anyway.
Yeah, so look at where we update the values. Here, this is how we get the new state value. So this is the old state, this is the new state. This is an addition. So before we were taking the old state, multiplying it by a weight and getting the new state. So when we were taking the derivative of the previous state with respect to, of the next state with respect to previous states, we were just getting a long product. Yeah, with a product that had a lot of weights in it. Because we were taking the Jacobian of each weight matrix, or the derivative. In this case, we are no longer doing that. This is a linear function. So that's one of the key parts of the LSTM. You might if you read about it, it might be called the linear carousel. Okay, so if in the diagram I mentioned before, this was the forget gate. We're basically multiplying each of the inputs by some value and then adding that to our cell state. It's called the forget gate. You can also, I think it could also be called the remember gate because you're choosing what to remember in the same, if you don't forget something, you're remembering it. This is the update step. So in the update step, we are taking the new input and adding it in some way to the old input. Yeah? In the final update step, we're choosing what to output to h sub t, which is our output at that time. Our output is different than our cell state, so we can choose to keep things in our cell state but not output it. You might notice they all look really similar. That's because all of these things are just deciding what to output, what to forget, based on some function of the input and the previous cell state. So based on like what I've seen before and based on what my new input is, I can decide what parts of the previous stuff I want to keep, what parts of the new stuff I want to keep, and what I want to output.
Is there a reason why the update function is so complicated? Well, because you see how you use 2 different sigmoid.
So yeah, so we basically, so we want to, it's because we want to keep certain parts of we want to update certain things, but we also know the amount by which we update it. So in this part, we're choosing what we want to update, and in this part, we're choosing how much of each of those things how much we want to scale each of those things. So that's why there's this additional multiplication. Does that make sense? So here we're choosing like which parts of this new input we want to update to the cell state. And in this part, we're deciding, this is basically a scaling factor, where we're deciding how much of each of those parts of which we decided to keep we want to update. So we can scale them up, scale them down based on how important they are. And that's that additional multiplication, and then that update thing is then added to the cell state.
So basically, all the hypertangents are like fixed, like rectify you really need it. The other ones, like people like experimenting using different rectifiers.
Sorry, could you repeat the question?
Oh well, because it seems that like the hypertangent definitely has to be within between 0 and 1. But what about the others? But what about the sigmoids? Can they be a value?
So the sigmoid literally means sigmoid function, so between 0 to 1, yeah.
What's the support bracket notation? You have 2 vectors inside.
It's like the aggregate of those 2 vectors, so like concatenated together. Yeah. Mm-hmm.
So the vanishing rate is mainly a gigantic product of things that are less than 1, right?
Yeah.
How does this avoid that product?
Okay, so first of all, like I mentioned before, since our update is a linear update, it's not a multiplicative update. We're not multiplying. There's not a derivative of s sub n to s sub n minus 1, which was where all those tiny numbers were coming from. We don't keep, there's not a repeated weight matrix in there because our update is, where is it? It's that one that says C of t equals this. Yeah, I'm not sure if that's clear, but yeah, okay. So the other thing is that there's no activation function here. So like, let me try to come up with an example. So say that for a given input, say that our input at time 0, the forget gate activation for that input was a 1. So the identity, basically. We multiplied it by a 1, so we kept it completely in our cell state. And say after that, it never got updated. In that case, when we take the derivative of the loss with respect to that, it'll completely be 1 because we only ever multiplied it by a 1. Like when we take the derivative, it was only multiplied by a 1, so we would never, the activation function, the f function in that case, would be the identity. And so that input would contribute fully to the loss. And the weight that was multiplied by that input would contribute fully to the loss at a future time step because there is no small activation function. And basically, you can think about the activation function in an LSTM is whatever the forget gate activation is. That's what we're multiplying our new inputs by when we, that's what we're multiplying our cell state, the values in our cell state by. I guess since it's past the hour, I should at least start this or let people start, and you guys can keep asking questions.
So part 4 is the tutorial. So if you go to this link here, there is a GitHub repo that you should download or clone, and then instructions within here on what to run. We'll be around answering questions and helping out, but it's a really cool lab, and we hope you enjoy it.